So I promised I would do a video to go over 5 of the questions from the practice exam. I had given a survey to try to find if what everyone found was their most needed one, but I'm assuming everybody else also is pretty busy. So I figured I would give you 5 questions that are right off the practice exam. Really good ideas to study these ones since they're a big part of the main portion of the test. So, a lot of what I'm looking for is to, have us see that we know how to handle graphs and be able to, apply equations in the right situations. So I picked a couple, and then I'll go through them. And if anybody has any questions, feel free to email me if something was unclear. Okay, so let's look at I picked question 12, 14, 16, 18, and 19. So question 12 says, a ball is thrown straight downward with a speed of 0.5 meters per second from a height of 4 meters. What is the speed of the ball 0.7 second after it's released? Okay, so a lot of words. And usually in this case, the first thing we would want to start with is our givens. Right? I find it's fairly helpful in these kind of situations also to draw a little bit of a picture, right? So in a little case here, draw a little ball, right? The ball is going downward, right? It's got a little bit of a downward speed, and the speed that it's coming down, it's VI, right? The VI is equal to 0.5 meters, right? Great. And it says from a height of 4 meters, so that means that if ground is down here, right, the ball is starting, the height of the ball, we'll assume from the center of the thing, right, the height of the ball here, this is going to be, we'll say that's 4 meters, right, that's going to be our distance, our initial distance at least, right? And then it says, the question asks, what is the speed of the ball 0.7 seconds after it's released? So what we want to do is we want to write out, right, that what we're looking for is the final speed, the speed, at that given time, right? So our final speed is what we're looking for, and the time is equal to 0.7 seconds, right? That's what it says. Okay. Great. So we've got a couple of variables, right? We've got the VF, we've got the VI, we've got the T. One thing that's a big theme in this test, that if something is falling, right, if it's falling down, get rid of that connection, right, because it's falling, right, if this ball is falling down, we know that the acceleration is going to be equal to negative 9.81 meters per second squared, right? That's the acceleration due to gravity, and that's always the case as long as the ball is near to the surface of the Earth and not on like a different planet or anything crazy like that. So we've got 4 variables. Distance in this case is just thrown in there to throw you off. You don't even need it. What you do is you go to your reference table, right? So take a look at the reference table, and we say which one, right, which one of these equations, let's see if I can shrink this down a little bit so it fits in a little better, right, so we can see both, right? We look at our reference table and we say, well, what equation over here has the ones that we have over here? So VI, VF, T, and A, right, well, right over here, the third one down, VF is equal to VI plus AT. Right, so let's see if I can shrink it, make it see it better. It's kind of tough doing this because Paint is terrible when it comes to typing equations. So I'm going to do this using Word, like a mixture of both. That way let's do it Windows. Okay, so I'm going to kind of like use both so that you can kind of see things a little better. Right, so in this case, the equation we want to use is VF is equal to VI plus AT. The reason is because the variables we have is VI, VF, T, and A, right? Okay, so let's go to that particular one. Right, I'm just going to copy it. Go down, give it some space. Right. So we're trying to find the final speed, right? So to find the final speed, what we can do is we can rearrange this equation so that we're looking for the final speed. Well, we don't even need to rearrange it. It's already set up the way it is, right? All we really have to do is plug in our numbers, right? So our VI in this case was 0.5, right? And that's meters per second, right? Our acceleration is equal to 9.81, and that is meters per second squared, right? And our time in this case, we said, well, the time is 0.7 seconds, right? So got that all in. Pull out the calculator, right? And so all I've got to do is take 0.7 times 9.81, so that's 6.867. So this new thing is now going to be 6.867. And then if we cancel, this is going to be just meters per second, right? Because the seconds here will cancel with the square up there. So that's just going to be meters per second, right? Okay, so we got that. Plus 0.5 meters per second. So finally, right? Plugging that all into a calculator, plus 0.5, we should have a final velocity that gives us, where'd it go? 7.4, right? We should get 7.4 meters per second should be our answer for the final speed of the ball after 0.7 seconds. Let's see if that makes any sense. Hopefully it does. Oh, and there it is, right there. Choice B, 7.4 meters per second, right? So a quick overview, right? Make the givens table, right? Identify which of the variables that you are given in your first questions. Then from that, look at your reference table, find out which equation here fits the variables given to you. Then plug in your values, and there you go, right? Pretty straightforward, right? I went nice and slow and steady in that case, but you know, on the exact exam, you got to work quicker, right? And make sure that you don't run out of time. Okay, there's one down. Next one on our list, we're going to do example 14. So I decided to also pick a bunch where I'm not so much, you know, messing with numbers here, because well, it's hard to do on this computer because it doesn't have like the pen like the smartboard. But so we'll just take a look at some of the questions and just do it that way, right? Okay, question 14. Okay, here's an easy one to do if you know how to draw it. So it says a child walks 5 meters north, then 4 meters east, and finally 2 meters south. And it says, what is the magnitude of the resultant displacement of the child after the entire walk? Right, so let's clear off all this stuff. Don't need any of that. Right, so the way to do this is to draw it again, right? You want to draw it using arrows and try to represent your drawing to show what happened. So we said a child walks 5 meters north. I just draw kind of like an arrow, right? Like this. Right, and that's going to be 5. Right, and then 4 meters east, right? So he then goes not quite as far. 4 meters east. And then finally, he goes 2 meters south. Right? 2 meters south. And then the question is, well, what is the full displacement? Like, what is the magnitude of the resultant displacement, right? The word magnitude means amount, and resultant is when you add all the vectors together, and displacement is literally the distance from the start to the end point. So what we do is we take another arrow and connect from where we started to where we ended. So what we're trying to do is figure out how far it is from here to there, right? Well, one way to do this would be to recreate it so that it's like a triangle, right? So instead of having it have this big lump in here, I could think of it as a triangle that's that far, right? That from here to there, right, is the horizontal displacement, right? And that doesn't change. That's still 4 meters, right? So I can even sort of grab that and bring it down, right? Now this one becomes a little tricky because it's not 5 meters anymore to get to that spot. This spot just here is technically the 5 meters minus the 2 meters that you went south back towards where you started. So instead of 5 minus 2 gives us 3 meters. Let's do that using black. Right? 3 meters. Right, so basically what we've done now is we've recreated the journey using a picture, right? And by making that triangle, we now see that to find that third side, right, that unknown side, basically it's Pythagorean theorem, right? But if you're, know your math things, when you have 3, 4, it's considered a special right triangle. This is called a 3, 4, 5 meter right triangle. And so for this case, since you end up with 3, 4, 5, your length, your horizontal displacement should be 5. Is that a choice? Yep, there it is right there. 5 meters, right? Great. Okay, so we got 2 down. 3 more to go. Number 16, right? Okay. So number 16 is a vector question. It's asking you basically, what happens when you combine 2 vectors, right? So vectors basically, when you graphically add them, they kind of change the direction and how much the arrows are, right? So the question says, which force vector B below could be added to force vector A to produce resultant vector R? So if we sort of thought about it, let's get rid of this one. Try to sort of see if we can kind of recreate that thing down over here. So if I've got a vector like that, right, kind of looking like this, right, and then we're going to call that, let's see if I can make this bigger a little bit. It's kind of ugly. R, right? So this is vector R, right? So we were trying to figure out what vector could be added to force A to produce resultant vector R. So to figure out which vector can add to A to give you R, we've got to take a look at what would happen if you sort of drew them, right? So if I take the example down here, I'm just going to recreate them to make sense. Right, so this one that's going out, right, that's our choice, that's A choice, right, choice A. Right, so we're going to kind of extend that outwards like that. That's choice A. Choice B says that the vector is going back like that, choice B. Then C choice is saying that the vector is going down like that. That was our C choice. And then D says the vector is going out like that. That's our D choice. You always got to remember you draw it from the origin point where all the vectors kind of connect. So now it's actually kind of a tricky thing, and another hard part about this is that I've sort of not drawn it exactly to scale. So I'm going to kind of have to just kind of explain it kind of freehand. If we look at this vector, it would take A and bend it. Well, you change it. It would bend A in this direction, right? So this one's not going to cut it, right? Because we don't really want to bend the vector this way. We want the vector to go up towards R, right? That's the goal here. This one, again, is going to bend this vector down towards B, which still doesn't make any sense. So basically that leaves us either choice A or choice C. Now, basically what we use is something called the head-to-tail method. That if I took the one vector, and let's see if I can do this, should be able to select like a freeform shape. If I took this vector down here, right, it's going to look ugly, right? If I took this vector and I put it to the head of the other vector, the endpoint of that C vector is where the resultant would come out. Right, so this obviously doesn't make any sense because that's where the resultant, where I'm pointing is where the resultant we want it to be. So if we had took the C and attached it up to here, it's not going anywhere near where we want our resultant. Now, if I do it with the A vector, right, same idea. I'm just going to kind of cut it out of its current spot, and I place it up here. I mean, it's not perfect, but it's the closest one to actually filling out, completing the vector. So in this case, the one that we want to choose would be the choice A. Right? Choice A is the one that if I combine it with vector A, it'll give me, choice R. Okay. 16 up to 18. Okay, so 18 and 19 doesn't really require me to do any, messing around. It just sort of verbally explain. Right, so basically you guys have to be able to recognize a motion of an object in equilibrium, and the key word equilibrium, right? Equilibrium, right? It means that it's moving at constant speed, right? That's a huge concept in physics. You have to understand that whenever you hear the phrase equilibrium, it means that the object's in the state of constant motion in terms of constant speed. Now, that constant motion could appear to be sitting, right? If you're sitting, you're technically at a constant speed, or you could be cruising on a highway going 50 miles an hour and still be in equilibrium. But the point is that equilibrium means constant speed. Now, if I look in the choices given here, right, this guy, let's go to the bottom, right? So this one, velocity is changing. So right off the bat, that's not going to be it. This one, same idea, velocity changing, right? Not going to work. This one, right, has your displacement in time, but the thing is, this rate is a constant increase of position, right? So if your position is flat, right, like this, it means you're going at a speed, but it's a constant speed. So this one, right, means that if it's curving in displacement, this is a case of acceleration. So choice B, acceleration. D, really crazy acceleration. C is also acceleration. The only one where it's got a constant speed, that's choice A. Right, so choice A would be the correct one for 18. Last one on our list is number 19. Which paragraphs represent the same motion of an object? And like these questions, you basically just look at them. Look at them one at a time and see if they make any sense. Like I'll go from the bottom going up. So displacement increasing and then going back to the beginning. And then the velocity graph is saying you're constantly positive velocity. That makes no sense at all. That just doesn't make any sense. This one, you're decreasing your displacement down to 0. But in this one, you're going negative speed, then stopping, and then going to positive speed. This doesn't make any sense either. This one, you're starting negative distance. You're going to 0, then you're going to positive distance. But in the velocity graph, it's constant negative velocity. So if you have negative velocity, you're not going to be increasing your displacement positive. That just doesn't make any sense. So the last choice, you can see that the displacement is curving up. And that curve comes from the fact that you're changing your velocity, but a positive way. Whenever you see an increasing in your velocity like this, your graph should have a curvature to it. The only other one here that's curved is the bottom one, but the curve doesn't make any sense because it's a constant velocity. So the end answer should be A for choice 19 because you're increasing your speed and it's showing that accelerated motion for the displacement. So I hope that helped. I tried to keep it pretty short. Like I said, if you have any other questions, try to email me, and best of luck for tomorrow.